Okay, so this video is going to be a little different. This one's going to be not connected to any particular topic. This one's just going to kind of be a general overview of dilations. Okay, and so dilations are one more type of transformation that we haven't talked about. And the reason why we didn't talk about it with the other ones is technically dilations fit into a different type of transformation. So all the ones we've done so far mathematically are what are called rigid transformations. Okay, and so basically all rigid transformations means is it just means that the shape that we moved around using whatever, whether it was a slide in a translation or a flip in a reflection or a spin in a rotation, the shape stayed congruent. Okay, and that's going to be a key word for us today. So remember that congruent is just kind of a geometry word for, oops, that was a really ugly equal sign, for basically equal. Okay, so the word congruent and equal are kind of, they're slightly different, but essentially they're almost the same. Okay, so we have been doing rigid transformations, things where the object doesn't change. Okay, a dilation is an example of a non-rigid transformation. Okay, and so what that means is that in a dilation, the shape will not be congruent. Okay, you will not do a dilation and keep a congruent shape. Okay, instead, what we're going to have are what we call similar shapes. Okay, and so similar now in English means, you know, that they're close together, they're like each other. Okay, in math it has a little more specific definition that we're going to get into just a little bit later. Okay, so let's just do some basic overview of what we see when we see a dilation. Okay, so I have put a triangle here. I promise it's not going to stay this ugly brown because it actually turns out that this is actually two triangles. Okay, so right now I have a dilation, what they call a dilation factor of 1. So let me change that to something different. Let's put a dilation factor of 2, let's say. Okay, so what do you see with these two triangles? Okay, so the green triangle is what we started with originally. Okay, and I included a dilation factor of 2. Okay, so how we would describe this is the green triangle was dilated by a factor of 2. Okay, so all that does is take the values of the points in the green triangle. Okay, so in this case, 1, 5, 6, 3, and -5, -7, and just multiply those numbers by 2. So for example, the 1, 5, when I multiplied both of the coordinates by 2, turned into 1 times 2 is 2, and 5 times 2 is 10. Okay, and we're going to repeat that process for all of these. Okay, so my 6, when it got multiplied by 2, turned into 12. My 3, when it got multiplied by 2, turned into 6, and my -5 became -10, and my -7 became -14. You get the idea. Okay, if I multiplied by something larger, let's say 5, okay, zoom out a little bit so we can see it, the same logic holds. Okay, so my 1, 4 turned into 5, 20, my 6, 3 turned into 30, 15, because now I'm multiplying by a factor of 5. 6 times 5 is 30, 3 times 5 is 15. Okay? In addition to that, we can also, I'm going to make my green triangle just a little bit bigger, okay? We can also have dilation factors that are less than 1, so something like 1/2. Okay? If you look at a dilation of 1/2, it does the same thing, except now instead of multiplying by 2 or by 5, we're multiplying by a half or 0.5. Okay? So half of -2 gives me -1. Half of 13 gives me 6.5. Okay? So basically dilations are going to stretch or shrink the shape, but notice the shape is still the same basic triangle, right? They still look essentially the same, just one is bigger than the other. Okay, and so that's why these are what are called similar triangles. Okay, next thing, let's look at what this would look like as an algebraic representation. So if you remember back to the last video on algebraic representations, we always start with x comma y. Well, in a dilation, what are we doing? So let me change it back to a non-fractional one, although we can do it with a fractional one. We will in a second. Let's change it back to our simple one, where the dilation factor is 2. Okay? So what did we do with our first point here to turn negative 213 into negative 426? Well, we talked about how we're multiplying by the dilation factor, which in this case is 2. Okay? So, for example, if I wanted to write the algebraic representation of dilating by a factor of 2, I would take the x-coordinate over here, multiply it by 2, and the y-coordinate and multiply it by 2. Okay? If I wanted to dilate by a factor of 5, because we did that one earlier, that would be, again, start with x comma y, and then it would be 5x and 5y. Okay? And similarly, if I wanted to dilate by a factor of 1/2, same idea. Start with x comma y, and then 1/2 x comma 1/2 y. Okay? Because I'm taking my original points and I'm multiplying them by whatever my dilation factor is. Okay? And they're going to give you this number. Okay? Because it's going to have to, or you're going to have to calculate it and they're going to give you the points. Okay? All right. So that's the basics of dilation. Now there's one other idea that we need to talk about. Okay? So, and that is with these similar triangles. So I'm going to draw two triangles that are roughly similar. And again, forgive if my drawing is not quite perfect because, let's be honest, there's a reason why I'm not an art teacher. Okay? So I'm going to call this one A, B, C, and my smaller one. And I'm going to say this bigger one is the dilated version, A prime, B prime, and C prime. Okay? So I can use, if I was given, let's say, the sides of this triangle. So let's say this one was 2, this one was 4, and this one was, let's say, 5. They look almost the same, but let's just make them different for the sake of doing this. Okay? So let's say, and then this one, let's say it has a factor of 3. This one would be 6, and I want to know the missing side here. Okay? Well, these sides are related. Ooh, hold on. I need to change my labels here real quick, just so I can make them match the other ones. This would be A prime, B prime, C prime. Sorry about that. Okay, so one thing I want to just touch on, just so I can make sure that you guys see why I made that mistake. You need to make sure that your points actually match up. So A needs to match up with A prime, B needs to match up with B prime, and I was being a little careless and didn't pay attention to that. So just watch out for that. Okay? All right, so now we can set these up as ratios. Okay? So I'm going to put the measurements of AB over the measurements of its prime version. Okay? So in this case, that is 2 over 3. Okay, I'm going to leave that as a fraction for now. Okay, now let's look at CB. I'm going to do the exact same process. I'm going to put the measurement for CB on top, just like how I did with AB on top. And then I'm going to put C prime and B prime on the bottom. And if I match that, that is going to be 4 over 6. Okay, and if you're paying attention, you can reduce this 4 and this 6 by dividing both of them by 2, okay? And if I divide both them by 2, I end up with the exact same ratio of 2/3, okay? These ratios always hold because of similar triangles, okay? So, well, I don't actually need to go through and do all this process for all of the sides. I just need to do it with one of the sides and then the one that I don't know. So if I look at AC, well, AC over A prime C prime, AC is going to be 5, and A prime C prime, I don't know yet. So that's going to be my X here. Okay? So, but based on what the conversation we had earlier, I know that this has to equal 2/3. Okay? So from there, I can actually answer this problem. Okay? So if you remember, the easiest way to solve a problem where two ratios are equal to each other is just to cross multiply. Okay? So we're going to take our x and multiply it by 2 and get 2x. Okay? That is this diagonal. Okay? And then I'm going to take my x and my 5 and multiply it by 3, and that's going to be my other diagonal. 5 times 3 gives me 15. Okay? Once we've done that, we simplify the equation dramatically, because now all I have to do to figure out what x is divide by 2. Okay? So that means that the answer to this problem is x equals 7.5. Okay? So basically, if you know that two triangles, or two shapes, I should say, are dilated, okay, are versions of each other, you know that they are similar, which means you can set up ratios. Okay? Now, the one thing you want to make sure of is notice, okay, I did all of the originals on the top, and I did all of the primes on the bottom. Okay? Now, you don't have to set up your ratios in that exact way. You could set them up using a different pattern. So, for example, I could have done A prime, B prime over AB. Okay? But if I did that, then I would need to be consistent with the other one. I would do C prime over B prime over CB. Okay? I would have to keep it the same throughout the entire problem. Okay? So just make sure that whatever pattern you are setting, you're going to stick with that pattern throughout the entire problem. Okay? All right. That will do it. That's basically all the basics of dilations. And we're going to go, I'm going to do videos for the actual problems themselves as well. But this should give you kind of a good place to start. Okay? So for all the dilations problems, I would recommend kind of starting here.